Welcome to the Accellera Standards Technical Update. I'm Uwe Simm from Cadence Design. I'll be talking about UVM updates. And then we have Sharon, we have Erwin, Kock, and Philipp doing on SystemC and IP-XACT. Basically, we have 4 parts here, UVM and IEEE 1800.2. That's me. We have portable stimulus. Sharon, Erwin is doing IP-XACT. And the 4th point is SystemC. So it's kind of a high-level update, what we're going to do. It's not, really diving deep into all technical details. For UVM and IEEE 1800.2, this is a presentation basically on behalf of the working group. So it's not just me doing all that stuff. There's a lot of people, a lot of companies contributing in that working group. And the first thing you see is, and it might be, a little bit new to you, even if it's called Accellera Standards Update, there's IEEE on that list. And I'm going to show you why. For UVM, if you're aware with the whole effort, UVM was developed, started 2000, maybe 2010 and so on. It's kind of the first version of UVM appeared, UVM 1.0 EA. And it was developed in Accellera. Accellera was basically the standards body to develop the standard and the library, basically the class library. The two things come together. The standard being the Acrobat document, the PDF document, and the library in System Verilog is basically a System Verilog code class library. The two things being developed under the Accellera roof. And that happened till about 2014, which is last year. The last version developed under that roof is UVM 1.2. One of the charters in Accellera is to provide basically material towards IEEE, and it's going to happen now. So basically we're forking now. The standard portion of UVM, the API definition, the document, the PDF, is developed in IEEE. And it's a working group under the 1800.2. There's a working group for that. And hopefully it will result in an IEEE standard. Saying that IEEE deals with the standard itself, it deals with the PDF, it also means IEEE will not produce a class library for you. What's going to happen is that Accellera is continuing the effort and will produce a compatible reference library for that above UVM standard as part of their efforts. So Accellera will provide the reference library, which matches the definition of the IEEE standard. That will happen. And that is actually where we are right now. We are right now in this transition phase. So basically we're splitting up. And we do hope basically that by mid of next year, we will have the two things in place at the same point in time. So we will have an IEEE standard and we will have a reference library provided. This is the high-level picture we focus right now on. The deliverables of the whole process is, first of all, 1800.2 means it is a System Verilog focused effort. So this is not a mixed language or a SystemC focused effort under that IEEE roof. It's a System Verilog centric effort. And the effort aims to define a functional API, not an implementation. So we're going to define an API which lets you verify things, but we are not just documenting the current implementation of the UVM class library. So we're moving an abstraction layer higher than just implementing things. We will produce the LIM, basically the effort results in that PDF document, which is basically voted upon and it's basically shared very, very much like an IP-XACT standard or VHDL or System Verilog standard. It's the PDF you can use as a reference. And as I said, we're trying to raise the abstraction level slightly. That gives room for multiple implementations. So the standard is the standard. It defines an API. But under that standard, you might have different implementations of that standard. One of the implementations will be the reference library. But there will be others eventually which satisfy the same standard, but it's kind of, different implementation, smarter implementation, better memory footprint or whatever. That is the focus in IEEE 1800.2 in the working group. The Accellera working group, which used to maintain all of that in the past, will deliver UVM System Verilog reference implementation. So it will evolve the current library to match the IEEE standard, and it also will provide bug fixes for the UVM library. You see above here, the standard itself is not bug fixed. This is not the software development process here. This here is releasing software. If you or your company want to contribute to that process, either in the definition of the standard in IEEE or in Accellera in the implementation and in the bug fixing, then you basically got two options. So the first option is you contribute to the working group, to the IEEE working groups. That's open for all the IEEE members, and there's a call running every other week at 9 a.m. PST. 9 a.m. PST is 6 p.m. here. So if you want to contribute, you can provide proposals, you can review the things, you can just monitor the things which are coming. If you already know that there are things which should be in the standard, you can also go to the Mantis Hub. All the issues, all the problems, all the things we should do is tracked in the Accellera Mantis Hub. So every item which should be addressed is captured there. You go to the 1800.2 section and basically you open a Mantis item that, registers should be that long and that wide or whatever. Whatever you feel is missing or lacking from the standard today and is not captured, let's say, by the discussion in IEEE, you can basically add a Mantis item, you can have it discussed, and basically then it either makes into the standard or not. For Accellera, it's basically they also meet every other week, basically interleaving the two calls. Again, 9 a.m. PST, 6 p.m. here. And the issues in Accellera, basically typical bug fixes or implementation problems of the actual class library is also tracked on the Mantis Hub, and you just select the UVM section there. The general focus area, why we're going and what we are trying to accomplish. The first point, we try to get more flexibility. We're trying to get away from a particular implementation. We try to find an API which gives us more options for future implementations. Just to name one thing, when we started UVM, we did not have interface classes, for instance. The way we defined a new standard opens up the opportunity to implement that standard with interface classes, giving much better footprint and memory and so on. We're also trying to remove implementation artifacts from the LLM. If you're aware that, from the whole history of UVM, it comes back from AVM and ERM days, it got merged, became OVM at some point, and it got merged with what came from VMM, and then we went over UVM 1.0, UVM 1.1, UVM 1.2. So there are a lot of implementation artifacts in the library. And what we don't want to do is we don't want to carry over these artifacts, this old stuff. So that's why we're going to remove these artifacts from the LLM. They might still exist in the library, but they are not part of the official UVM standard. We also do review the API, so for backward compatibility, consistency, so whenever there are a couple of ways to accomplish the same, we're trying to cut that down to one way or a safe way to accomplish something, not invent 100 ways of things. We're trying to simplify things, and we try to build the API in a way that we do have a core which can be extended without touching the core. As of now, UVM is pretty monolithic, right? So it's a big class library, and if you want to change something which goes a little bit ahead, you might end up changing the library, which is bad, right? So the class library should not prevent you from doing additional things you didn't think about, but this needs to have proper interfaces. And this is something we are currently looking at. And obviously, really important, we need to fully document and describe the API, not just this is function call, this is the signature. We also need to document what is the semantic of that call, right? So what should happen, and eventually what should not happen, or what are the guarantees? Is it random stable? Is it not random stable? Are you guaranteed to get a queue always, in a guaranteed order of elements or not? So there are a lot of things in terms of what needs to be standardized in the document. And obviously, if you're scared by all of that, by all these changes here, the library itself, the code base you're getting from Accellera, the library can still support deprecated things. The library can still decide, this is the IEEE version, but I'm still giving you an option, that UVM 1.2 is essentially more or less supported, right? So there's a difference between the standard itself, what the standard says, and what the library may do in addition. We're currently talking about opening 2 sub-working groups under the roof of the 1800.2. One is the register working group, because it's a pretty big thing and it becomes more and more in terms of SOC scenarios, and we see there's currently kind of a lack of functionality or definition. So if you want to contribute to that, or if you have seen issues there, I just list 4 things here. So we need to identify and close the current issues which are already known. We want to move ahead with the definition of additional API, which is required especially for dynamic SOC use models. So we are not currently, if you are deeper in UVM, currently, if you look in a register space, it's pretty static. You just can create the address map once and then that's it, right? But most of the current SOCs, basically you change the addressing, you remap some address map to some other place, you change the routing, you have remap states and all of that. So we want to align with these use models. We want to align with other relevant standards, especially IP-XACT there, because a lot of the terminology in UVM Reg is IP-XACT based, but not all of it. You know, we want to benefit from the definition already made in IP-XACT. We don't want to invent things on our own. So we should align, makes our life easier in terms of describing what we want and makes basically the mapping between the 2 standards easier. Currently, we're in issue collection and prioritization. So if you're having issues, raise your hand, contribute, let the committee know, let me know, so basically that we can fill it in, because at some point in time we need to basically sum it up and then we can basically address the most burning issues. Very similar thing happens in the proposed TLM working group, and the targets there are to align the UVM TLM with the current IEEE 1666 TLM2 concepts. We have something in UVM we blindly call TLM. It sounds and it smells like it is TLM, but you know, if you carefully look at the differences in the standard, in the SystemC standard, there are differences. There are lacks in implementation, there are differences in semantic, and the question is, what can we unify? Where can we unify? Where do we differ, just for implementation reasons? And obviously, all of these differences, they need to be put into the documentation. So we need to explain execution semantics, the underlying concepts, all of the things which have not been present in the current standard document as of UVM 1.2 from Accellera. And obviously then there's the question, is the current TLM API, is it complete? Is it worth expanding that? Or is this, for the UVM world of things, is that good enough?
Anyone knows what the portable stimuli is? What is it that we're doing there in that working group? Okay, quite a few. It's pretty good. So our goal, when Uwe was talking, it's kind of reminded me of the initial days of UVM and maybe even the initial days of using randoms for verification, 95, 96, when we approached test writers and told them, hey, don't write the addresses with your own fingers. Let the technology do it and use constraint for that and use coverage to know what was done. This is as big. I think it's going to affect the life of many of you here, the working life of many of you here. On the way you're going to do things. What we're defining at this point is a language, but it's sort of a dream language, you can say, after all that period of time. We're talking about goal-directed. I want these 2 things to happen at the same time. I want this event to take place. And the semantic of the language allow tools to solve that, take that request and make sense of it and find the solution, even if there's sparse legal space. So even if the solution is very hard to find for us as humans to, I need to use this configuration, I need to use these delays and these events to make that event, that goal event appear, the language allows to build technologies that will solve that will find this thing. It's enable maximization. Currently, if you create coverage, you do randomness, etc., then you want to have some kind of maximization. We're talking about real maximization, not just the input space and say, hey, fill that up and don't create a lot of redundancy. I want to control the redundancy. Sometimes I do want redundancy. We enable that. We allow that to take place. Coverage reachability. Tell me, is that legal? Is that possible? The tool will tell you, the tool could, on top of that semantic, to tell you it's not. Here's why. This is impossible to get that use case that you want. That's what we're talking about here. The other thing is making better use of your investment. We're talking about all platforms. So simulation, virtual platform, acceleration, emulation, post-silicon, all platforms. These are real tools that are used today. We just create a standard out of it, combining the best ideas and concepts from all these tools. Again, we're working very close to mentor exactly like we did in the UVM days, and there's a group as well. So, enable value and automation for individual teams. We're going to take the solvability, the expressiveness to the next level. That's what we're doing. So we're not asking just for portability, use us. The name is a little bit misleading, not just for the portable aspects. You're going to get a lot of value. Each individual team is going to get a lot of value out of this. And then allow sharing and executing scenarios across teams, across platforms, etc. As was mentioned in here. We're talking about SOCs, right? Multi-core, talking about software layers, below the operating system, above the operating system, synthetic testing, but above and below. So the scope is wide. And we're going to define a clear and robust semantic for that solution. So, there's the E versus Vera in the past, there was OVM versus VMM, etc. And at some point we converge, but there's a lot of casualties on the way that had to desert what they did and to adopt a new thing. So we're going to build it right from the start to be robust, to have a well-defined semantic. So a lot of tools could be built on top of that standard. Group info, this was officially formed December 15, 2014 by the Accellera board. We did have a proposed group just to make sure that there is enough motivation, there's enough contributors that want to be involved, and that was successful. The chair is Faris. I wouldn't be able to say the name, so he's a great guy from Intel. He's our chair, fearless leader. Tom Fitzpatrick from Intergraphic is the vice chair, and Tom Anderson from Brecker is the secretary, and we have multiple participant companies, Agnes Altera, AMD, Amic Analog Devices, Brecker, Cadence, Cisco, CVC, Encore Semi, Freescale, IBM, Intel. I'm going to read all of them. You're doing great work. Mentor Graphics, NVIDIA, Qualcomm, Semaphore, Sonic, Synopsys, and Viavia. All of these are involved. We're actually doing a lot of work. I attended a lot of these standardization bodies, and there is a lot of deep technical work that is being discussed. Here's the vision. This is what we're trying to achieve. So we have multiple users, and all of them try to do their job. The job is different. They have different focus. They have different terminology that they use. They have different amount of cycles that they use, different level of abstraction. It's all coming from the same spec eventually, but they do have different jobs. And what we want to define is some kind of an input format that will enable all of this. And that's what we do. We define a language. I'll show you a little bit of the details. A language that allows you to define use cases for SOCs, for IPs, etc. We take in mind or in consideration visualization. Can you visualize those concepts so people could share some kind of diagrams or charts between them to enable a discussion? That will go into some kind of tool, which vendors will build, and eventually will generate tests. So we're talking here both on generating ASCII code, right? So unlike UVM, for example, right? Here we're going to generate ASCII code, like instead of you typing with your own fingers, the tool will do that. But also on the fly. So you also have the kind of control working online with the execution engine, etc. So we're talking about both. Talking about the scope, I mentioned that. We're talking all the way from IP, simple IPs, though, if you just have random traffic that you need to shoot at some IP, probably that's going to be an overkill. There is some value, but maybe an overkill for what you're trying to do. But very quickly from subsystems that are a little bit more interesting, rather than just shooting data at it, you'll start seeing values, bare metal, software layers, etc. This is all part of the scope. And we're talking about all the execution engines. So this is really like when I said the flashback about how it used to be. We come to post-silicon guys and we explain, this is what coverage is. You can have gen-time coverage, you can have runtime coverage. That's, for them, it's this is what constraint is. And a lot of people, when we talk about SOC and creating use cases for SOC, they're saying, oh, you don't understand. You must be directed for that thing. That's why it's so unique. It is hard, and I think we're doing it. So the proposed working group, we collected a lot of requirements, 117. We categorized them, we prioritized them, etc. I'll show you a mind map of them, like constraint, inheritance, reuse across platform coverage, etc. But I think that was a big difference, of, at least for what I experienced in standardization. We actually created usage example to define the problem space. What are the typical usage examples that are out there? So we have 14 concrete usage examples contributed by users and by vendors that really define, here's the challenges that I have, the different challenges. Of course, there's more than 14 usage examples out there, but these are representative for typical issues that you may have. I'll show an example of that as well. So we did all that work. It was well defined, and also the contributors were supposed to show how they can resolve each one of these unique usage examples. Okay? So that could also be the base of later on to create some kind of compliance suite, etc., just to make sure that if you can run these, then you're good. A little bit about the requirements. Not going to go too much into details, but there is the portability, the users themselves, the platforms, integration, portability, the specs, the language itself. Some people have, I want to have these templates in the language, or this level of requirements, use cases for coverage checking, generation. This is just organization. You see, we took visualization into account. How would it look if you try to visualize it? What's the best input format that would allow visualization, etc.? So a lot of aspects were discussed here. Here's the usage examples. I have a few out of the 14. So you can see it covers the entire spectrum, starting from multi-core, doing coherency, cache, I/O coherency, power down the core, power up the core as you do so, etc. This is just one use case, important one for the mobile industry and for others, more and more today. Pad selection. We have all these pads and rules, and some of the configurations, some of the combinations are legal, some are not. You would like to try all of them. You would try to try a few of them. Make sure that you really exercise the right functionality in that specific configuration. Show how you can do that. And again, these are things that are hard to implement if you try just to use constraints, structs, etc., right? Because if you chose a pad and now you move to the next pad, etc., you might have just wasted the only path that could help you on the previous generation. So we're talking here about, here's what I need in a declarative way, and the technology should find a way to achieve that, but it's taking a lot of constraint and a lot of attributes into account. It's not one randomization at a time, right? Like we do with, let's say, sequences, right? You randomize this, and then you randomize this, and maybe another packet or call another subsequent. But here, you take everything into account. You take the configuration into account as well, because if you can create a path and the configuration does not match, then that's also not going to fly. So that's what we're talking about. And resource allocation, DMA channels, for example. Can I use all the DMA channels at the same time? That would be a nice request that I can, and then create one scenario that does it, random scenario that does it, and show me what I got, and maybe I want to do coverage on it. Can I use all the cores at the same time, with all the channels at the same time? These are the kind of things that we want to enable, and that's what exists in the user example. Video processing pipeline, exhaustive exercise of power state. How would I do that? If you're talking about a sparse legal state, I just want to cover, I want to visit this, then this, then this. Is there a way to do that directly or indirectly? Add transitions that I didn't think of to get from here to here. And all the way down to Ethernet controller. I just have an Ethernet controller. I want to try it out. So we basically define typical examples, but also define the spectrum and the space and the scope in which we're going to work on. So this is very interesting because now each contributor doesn't need to show, well, I can do inheritance, I can do classes, I can do randomization, choose me. Now you need to show how you solve industry challenges. Here's where we are. Did a lot of work. We're talking about the pre-working group that has started on March 2014. We formed the group itself, collected the usage example, call for contribution that happened in the middle, still collecting, getting more and more. At some point, more users got involved and start sending more of their challenges, which was great. We here on the contribution vote, actually I didn't update the slide. We had a contribution vote basically for formal reasons, procedure kind of reasons. We just accept all the contribution because we basically want to choose from all that spectrum to create the best solution. There was legal issues. If you're going to reject it, then we cannot do anything with it. So if someone is telling me, hey, my contribution was selected to be the standard, he might be right because we just took everything at this point. We are working on a draft standard that's going to be on May 25th, and on January 17th, we're going to have a first release of PSS, Portable Stimuli. That's the roadmap. These are the contributions. I'm going to talk a little bit about the collaboration. As I mentioned, we worked a lot, Kenneth and Mentor, and Breaker kind of joined as well. And we submitted a language, but don't think it's not a language you'll see. It's a different concept. I want to talk a little bit about that. Different concept than what you used to define those use cases and scenario. But it is a language, and the language features talks to the intuition of system Verilog users and C++ users. So the syntax looks the same, the constraint, the coverage, all look the same. We just took whatever is there, and we invented only when we had to. So that is one contribution. Breaker also submitted after that some kind of a C++ library, tried to achieve their own thing. This was considered with the usage example. Usage example were great serving for that purpose. It didn't meet the requirements. They were asked to, and took the action item, to add value constraints and coverage to their contribution, and then see if they can resolve the usage examples as well. So that is another contribution. Viabia and it's related to the register discussion that was here. They contributed an interesting thing, and I don't know how all these register descriptions eventually converge, but they have a solution in which you start with a register description, but they have also libraries and other attributes for sequences and the role of those registers, etc. And they can generate firmware or driver routines, so below and above the operating system from that starting point. So they thought, you could think about the problem as two-stage problem. One is to create the firmware routines, the building block that you're going to call, and the other one is to call them at the right time to create use cases and interesting scenarios. So that's what they contributed. So these are kind of the things that are being considered. All of us are working together, vendors and users as well. We have a lot of understanding by now of what it's going to be. What are the concepts? What is the character of what we're doing? So we're talking about combining constraint model-based approach and graph approaches. For those who've seen graph approaches, it's not decision graphs, the graphs are the same, but graph usage of action to capture the legal space. So basically, action is a piece of behavior. It has an input, which is things that need to happen or things it needs to consume, that behavior needs to consume something before it can operate. It has results of running that behavior, and there's resource requirements as well for that action to take place. So from that declarative description of actions, what they need to consume, what they produce, and the resource you have, you basically describe the scenario space, what is legal and what's not. A tool can read all these behaviors. Now you can come and say, as a scenario writer or test writer, to say, I want this after this and in parallel that. And the tool has enough knowledge just from those inputs, outputs, and resources to tell you, okay, here's a solution. I can even auto-complete what you ask for in a legal way. Or no, you cannot do that because you don't have enough resources for these behaviors that you ask for. Okay, so you come and you describe your scenario, the tool can auto-complete it, or can tell you, no, it's not. So that's what we have in mind. These are very modular. You don't know how many resources is going to be. That's up to the integrator. You don't know what memory you need to consume, etc. So very modular. You don't know who's going to provide that video or that memory buffer that you're going to read. You just put these actions together with their producing and consuming attributes and just talk to each other, start talking to each other and create scenarios. And we have value constraint, algebraic constraint as we know them, and path constraint as well to represent the model. So, from here, don't go here, etc. after this, don't do that. So this is kind of the overall solution that we have in mind. And there is a focus team. We used to have it in the OVM days as well. There is one weekly meeting that talk about all business and technical aspects of it, and there's a focus team that works on that collaboration and better defining what it means. One of the requirements that came up is making things more attractive for C++ writers. Is there a way to do that? Kind of things we discuss these days. By consensus, there is no vote. Here are two aspects of solution that we have, and they're pretty close to each other. One is to take C++ as a base, but add syntax to it, because we don't want to be limited by what GCC and G++ can compile. We want to have a good, safe language with coverage, with constraints, with all of these things. So this is one approach. As I said, it's more declarative in nature. You describe the behaviors and what they support and what they need, etc. Later, you can create procedural scenario and use case, but you have those declarative statements to either help complete what you ask for or tell you it cannot be done. That's in both cases. And the other part is basically creating a new language that will look like C++ or like System Verilog. So basically, this is the scope in which we're working with. We're into the summary. So assigned to capture all these concerns, portable similar, we're talking about generation, coverage, checking, visualization we're not going to produce tools, right? Visualization up to the vendors, but we're keeping that in the back of our heads. We're moving very, very quickly, actually very exciting work. And we have the milestone in May, the early adopter, 2016, and 2017, that's the first release. There are solutions out there. They show significant speed up of an automation and complementing what UVM does for those platforms of simulation and working beautifully on, embedded code with bare metal or post-silicon, etc. I'm a vendor, so I'm encouraging you to try and use those solutions right now. Just make sure you're not being locked into a non-standard solution or non-standard methodology. We already know where we're heading. The committee knows. If you want to know what's going on, you want to make sure that your needs are addressed, exactly like Uwe. I invite you to join the meetings that we have. There's more information about the website.
So I will be presenting an update on IP-XACT. In contradiction to the other two presentations, I will present the work that has been done and is available, not so much what we are going to do. So I'm working for NXP, but today I'll be wearing my Accellera and IEEE hat. So the topic of today is the changes that we have from the IEEE 2009 version of IP-XACT to the 2014 version of IP-XACT. The idea of the presentation is to give you an update on what has changed and why. So IP-XACT offers a standard structure. It offers you a structure to package IP. This is an IP-XACT term. What it means is that we provide you with a format to write an XML document that describes your IP data sheet. So instead of having a paper sheet, you can describe your IP data in an XML document that can be processed. Then you want to use these IP descriptions. So one of the things that you want to do is that you want to instantiate these IP blocks in your design and make a SOC or a subsystem. So we also capture that in an XML document. So you can instantiate your IPs and bring in connectivity between these IPs. And also we want to reuse these IP in tool flows. So we provide a tool interface, it's called TGI, Tight Generator Interface, which allows you to communicate with a database that supports IP-XACT. So this database will read in all these XML documents, and then with this tool interface, you can access the data that is in this database. So you don't have to write XML by hand, you can script it or you can program it. You can create new data, you can delete existing data, or you can modify data. So what does IP-XACT actually standardize? So in the PDF, in the document, you find what the schema looks like. So there is an XML schema that you can use to validate your XML documents. So there are different schemas. There are schemas for interface definitions. We call them bus and abstraction definitions. There's a schema to describe IPs, called components. And there are special IPs called abstractors. So these are basically the transactors that were mentioned in previous talks. There's a schema for describing designs. So that's IP instances and how you connect them up. There are schemas for design configurations. I will address that later also in the presentation. And there's schemas for generators. It's actually another word for tools. So you can invoke tools, and this XML document describes then where the tool is located and what input values you want to give to this tool invocation. Then there is a section in the PDF that discusses semantic consistency rules. So these are rules on top of what you can validate with an XML schema. Like an example that two registers cannot overlap. Simple example of a semantic consistency rule. And then there's the tool interface. So this is a defined set of messages that can be exchanged between a tool and the IP-XACT database. The intention of IP-XACT is to be design language neutral, but also programming language neutral. So we decided to define this interface in terms of HTML messages. In practice, a lot of vendors also offer a programming API in C++ or Java or Tcl to use this set of HTML messages. So what did we change in the 2014 revision? Well, an awful lot, so actually so much that I cannot go over it all. So I want to mention that, for instance, we changed the namespace from Spirit to IP-XACT. Maybe people remember that the first versions of IP-XACT were defined by the Spirit consortium, but this merged with Accellera, so the Spirit namespace was not appropriate anymore, so we changed it to IP-XACT. There are updates of the semantic consistency rules, and we also extended the tool interface such that you can do all XML editing that you need to do. So you can create, edit, modify all the data in an IP-XACT database. So for today I want to focus on 4 topics: parameter propagation, the expression language, conditionality, and view-specific port maps. And I also want to show how these 4 topics enable you to automate top-down design flows. So the first topic is parameter propagation. So this slide expresses what was available in the 2009 version. So in the 2009 version, we had parameters for components. So you could define a parameter or component C with parameters X and Y. And then when you instantiate this component in your design, you could set the actual values for these parameters. So in this case, we create X with 3 and a Y with 4, and that then could be propagated. So there was one level of parameter propagation from a component instance to a component, from a design to a component. So this was a bit limited, so we extended this quite a lot. So today you can specify parameters on all top-level elements, so not only on components, but also on design configuration, and on interfaces. Still, you have the components with parameter values, so if you instantiate a component in a design, you can set the values for the parameters. But in a component, you can also, again, instantiate a design, so this is a hierarchical component. And in the past, it was not possible to parameterize this design. So now you can do this, so you can make a new design, also parameterized, and the values that you give to these parameters can be an expression in the parameters of the component. This does not work only for designs, but also for interfaces. So you can parameterize your bus interface. Say now I have a bus width of 16, 24, or 32 bytes or bits. And the whole parameter mechanism propagates through the whole design hierarchy. So if you want, you can set all your parameters at the top and propagate them through the whole design hierarchy. The next topic is the expression language. In the 2009 version, the expression language was XPath. Reason to do that is that we wanted IP-XACT to be design language neutral. So we didn't want to make a choice between C, SystemC, VHDL or Verilog expressions. We want the expression to be design language neutral. Again, example, if we have parameters X and Y in a component, then you could define the width of a certain port by setting the left and the right value, and these values can be expressions in the parameters. And in 2009, we had to do this with a dependency attribute. So we said this left value is a dependency, and this should be an XPath expression. Because we now extended this parameter propagation mechanism, and the typical HDL designer is not really familiar with XPath, we decided to make this a bit more user-friendly. So we switched from XPath to System Verilog. So now the user can write expressions in System Verilog. And now we think that helps the adoption of expressions a bit more. So here you see that this expression is simply System Verilog expression X plus Y. This basically impacts all your XML documents. We have scripting to do the up conversion from, let's say, the 2009 version to the 2014 version to help you with that. But if you package new IP, you should be aware of the change in expression language. So other examples, 0x 1f becomes then tick h 1f. And also the concatenation of the ID of S and T divided by 2 becomes a bit simpler in System Verilog notation. Then the third topic, that's conditionality. And this is completely new in 2014. It didn't exist in 2009. And basically it means that the data that is present in your XML document can be conditioned by Boolean expressions. So almost all elements are now conditional. So on the right-hand side you see an example. Again, the same component C with parameters X and Y. And if you have a register description for register R in this component, then you can make the presence of this register a Boolean expression in your parameters. So depending on how you now configure your component C, this register is there or it is not there. So if it's not there, then all the sub-elements of this register are also not there. Also don't see the fields and the enumerated values and so on. Same holds for ports, for bus interfaces, for files, for almost anything. This is very powerful, but it also has some implications. For instance, on the semantic consistency rules. So some rules you can only check if you have resolved all these Boolean equations. 2 examples. If you have 2 registers, R1 and R2, then they cannot overlap, but you can only determine that if you know that both are present in your component. So in that case, that's limited to a single XML document. A more complex example is example 2. One of the rules is that you cannot have multiple drivers on an input port. So if you have 2 drivers, O1 and O2, which are connected to C1 and C2 through the input port, you can only check the multiple driver rule if you know that the output ports and the connections are present. This feature gives a lot of power in the sense that you can express a lot. It also brings quite a burden on rule checking and kind of the verification space that you have to deal with. Finally, I want to discuss port maps. It's one of my favorites. So in 2009, we could define bus interfaces. And what you typically do in such a bus interface is that you choose an abstraction definition. So that's a representation of the bus. And this abstraction definition defines which signals should be in this bus. So it defines the logical signals of that bus. So typically for an addressable bus, you have a clock, a reset, address, read and write data. And then what you do in the port map of such a bus interface is that you map the physical ports of your component onto the logical ports that you have in your abstraction definition. So each bit in your physical port maps to a logical bit on the logical ports, and then when you connect the interface, you know exactly which bits should be connected. So what is new in 2014 is that you can now have multiple of these abstraction types in your bus interface. So for the second one, I can choose a TLM representation of my bus. So probably that's a TLM socket. So I have a logical signal, my socket, and I have a physical TLM socket in my model of my component. And again, I map my physical socket onto the logical socket. So I have now two views in my component, an RTL view and a TLM view. Depending on the view that I select, I either get an RTL bus interface or a TLM bus interface. So this really now enables mixed RTL and TLM design. So for all my buses, I now can make an RTL representation and a TLM representation, and I can integrate my design. So I have here two component instances, I and J, with a master interface and a slave interface, which are connected through connection C. And this is one design. So I have one representation of this design with one connection, but I can now make 4 configurations of this design. So for each instance, I and J, I can choose which view I want to have. So in the first design configuration, called RTL, I choose the RTL view for both I and J. The idea is that you connect the blue side to the blue side, and because they reference to the same abstraction of my bus, I can simply connect that. The same applies if we choose the TLM view for both I and J. Then I have a yellow side and a yellow side, and because it's the same abstraction, I can connect that. The complicated cases, if I and J have different views selected. So if I choose the RTL view for I and the TLM view for J, then I need to have a special transactor on my connection C to do the abstraction conversion from RTL to TLM. And this abstractor is actually instantiated in the configuration. So it's not part of the design, it's part of a design configuration. And this abstractor is the result of the fact that I have chosen to select the RTL and the TLM view for I and J. Same applies for the other case where we go from TLM to RTL. So in this case, I would have one design with 4 design configurations, and from this single design, I can then generate 4 net lists using the 4 configurations. In the first case, it's all RTL. In the second case, it's all TLM. And in the third case, I have a part of my netlist RTL level and part of my netlist TLM level. And the abstractor or the transactor will do the translation from the signal level ports to the TLM level socket from left to right. In the last case, we go from TLM to RTL. Then I need a different transactor, but this transactor will do the translation then from TLM to RTL. So how does this now bring value to top-down design? In 2014, we can have a parameterizable design hierarchy with conditional elements and mixed abstraction levels. So on this slide, I just indicated 3 levels of abstraction, what I call block diagram, in which my IP block have views without any physical ports. So there's no physical interconnect whatsoever. Then I have a yellow color ESL design, and there my views have transaction level ports. And the blue part, I have RTL design, and then I have views with wire ports. And I can now mix and match these descriptions. So I could start off with a full design in white, which would be my SOC block diagram. And I would have described all of my registers and addressing in this design. So from that I could generate a UVM register model for each of the masters in the system. Or I could generate a system view description using ARM's CMSys format. And then I can start refining my design. So I can move some views to the transaction level modeling style. And then for that part I could generate SystemC interconnect and also generate SystemC register banks. And then I could move some parts of my design to the RTL world. And for that part I can generate signal level interconnect and detailed RTL register bank implementations. And finally I would end up with my RTL design, which would be ready for synthesis. Summarizing, the 2014 version is really a major update of the IP-XACT IEEE 1685 2009 version. So it brings parameter propagation, different expression language, conditional elements, and view-specific port maps that allow you to mix abstraction levels in the same design. And it brings you full tool interface support. So that allows you to make parameterizable design hierarchies with conditional elements, mixed abstraction levels. And the tool interface support allows you to program or script this completely. So you can automate your flow where and how you want with your own tools and scripts, operating on a database that is, let's say, vendor neutral, because each IP-XACT vendor should support the same TGI interface. So you could reuse your tools with different vendors. I'd like to acknowledge the IEEE workgroup members, especially Mark Knoll, who was our chair. He kept the focus and the time schedule that we had in mind. I also want to acknowledge all the other IP-XACT Accellera Schema working group members. Most of them were also in the IEEE workgroup, but not all of them. If you want to have more info, you can download a free copy from the standard through the Accellera website. If you want to have the real schema, you can also go to the Accellera website. There you can actually validate your own XML documents against this schema. There's additional material on IP-XACT provided by Accellera with examples, bus definitions, the conversion scripts from 2009 to 2014. We also have a forum where you can share your experiences or ask questions.
For the Accellera SystemC update, I give a condensed version and a higher level overview of what's going on in the SystemC world. The SystemC related standardization within Accellera is divided among a set of working groups, and these working groups are similar to what's going on in UVM, driving the IEEE standardization of the core language under IEEE 1666. So SystemC, as an overview, has a huge part which is standardized under IEEE 1666 with the most recent update in 2011. And the different parts are further developed within Accellera and always fed back to IEEE when there's time for another update. So here we see a graphical summary of the different scopes of the working groups. So we have the TLM working group working on transaction level modeling. We have the core language, the language working group building the foundation parts. We have the synthesis working group defining a subset for high-level synthesis. And we have analog mixed signal verification working group and CCI for configuration, control, and inspection, which means the tool interfaces to SystemC models. So for the language working group, which is defining the basis, we're currently working on incremental proposals towards the next IEEE update, which will likely happen later this decade. This is not fully roadmapped yet, but it's mostly depending on the amount of innovation when we have sufficient material that we start the IEEE process again. So we're mostly doing support work for other SystemC working groups and fixing bugs, recording errata for the IEEE standard. In the TLM working group, the activities have reconvened, now looking at additional protocol definitions beyond memory map buses, which was the original focus of the TLM working group. So they're currently looking at extensions to the modeling constructs to allow you the definition and modeling of additional protocols that are, for instance, serial protocols, bidirectional protocols, and do not follow the modeling style of the current TLM2 memory mapped.io focused standard. One aspect in this realm is, of course, also the TLM signal. How should a signal look like at the transaction level when you don't want to use RTL like SystemC signals? For synthesis, the biggest milestone was achieved in July 2015 when the current version of the synthesizable subset has completed its public review. Currently, the feedback is incorporated, and it is planned to have a release of the synthesizable subset standard in Q4 2015, and afterwards start integrating new topics for a second version of this standard. For CCI, the core focus is on the tool interfaces between the SystemC model and additional tools for simulation. This includes setting up your simulation model through configuration and also other interfaces like debug and tracing and so on. The current status is that the proof of concept implementation, which is available internally to the working group, is currently improved upon after a thorough review in the working group, and the plan is to complete these improvements both in the proof of concept implementation and in the accompanying LRM, and to have a public review of this language reference manual later next year. In the AMS world, we also had a significant milestone completed just recently, where the handover from this Accellera AMS, SystemC AMS working group to the IEEE P1666.1 working group has completed its ballot in the IEEE SA. And within Accellera, there are new features under development right now, including the piecewise linear modeling and customization of the tracing and additional analog solver parameters. So the immediate next steps are, of course, the full approval of the AMS standard of 1666 by IEEE, and then have an updated user guide published for all of you to ease adoption. Then we have the verification working group, which is currently mostly working on the native implementation of UVM in SystemC. We already briefly discussed it this morning. There's a tutorial right in parallel to this one, so you might want to look up the material if you're interested. And the plans for this work is to have a LRM, which has been completed, and a corresponding proof of concept implementation for public review either later this year or early next year, and then start working on standardization of coverage APIs and look into further explorations around SystemC and TLM when it comes to UVM. This was also mentioned briefly by Uwe, that there are inconsistencies between the notions of TLM in the UVM world, which has been also adopted by UVM SystemC in the first phase, and the original TLM definitions and methodology in SystemC itself. So this is also being looked at in this working group.